What exactly is chromatography? It is a separation technique. It is a technique that allows us to take a sample or a mixture and determine each of the individual components that make it up. Now, I always like to start with a little bit of history. Back in 1903, there was a Russian botanist by the name of Nikolai Sweat, and he wanted to determine what made leaves green. He used ether, literally chalk dust, and a glass tube. And as he ran his extract of the leaves down through the column, he saw colored bands. He coined the technique chromatography. Chroma, because he saw color on his white column, on his white packing, and graphy, because he literally used calcium carbonate or chalk dust for his column. In 1942, Martin and Singe developed or defined what is known as partition chromatography. And we are all familiar with that. We have all knocked a glass of water on a piece of paper and seen the black ink migrate into the various colors that make up black. Instrumentation did not enter the world of chromatography until 1952, when the same Martin, now working with James, develops gas chromatographs. HPLC really did not get its beginnings until 1958, when Spackman, Stein, and Moore automate amino acid analysis. And if you know anything about LC, amino acid analysis is probably one of the most difficult assays to perform. Now, when we talk about chromatography, we are talking about a family of techniques. The two main techniques, of course, are gas and liquid chromatography. But there is also a subcategory known as supercritical fluid chromatography. In gas chromatography, the mobile phase is a gas, and the samples we analyze need to be volatile. This only applies to about 20% of all of the known compounds that are out there in the world. So what technique then is going to allow us to separate the other 80%? That's where the world of liquid chromatography comes in. And today we're going to focus on liquid chromatography, and we're going to come down this tree looking at column chromatography and the modes underneath that. Now, what exactly is the LC chromatographic process? Well, basically, we're going to talk about two different phases, and our compounds of interest, or our analytes, are going to distribute between these two phases. So you're going to have the mobile phase, which is a flowing liquid, and then the stationary phase, which is a column or a tube packed with some type of support material. And your components are going to separate by differential interactions between the mobile and the stationary phases. These interactions could be ionic or adsorption or a weak carbon-to-carbon interaction. Now let's go back a moment and talk more about the technique that Nikolai Sweat first did, which is known as classic column chromatography. Here, as you can see, you have some kind of a tube. You add your sample, and then you slowly add liquid or mobile phase to it. By gravity, the sample and the mobile phase move down through the column, hopefully separating. You collect those fractions, and then you analyze them by some offline technique. Now, this approach of classic chromatography has some real advantages. It's inexpensive. Literally, it was a glass tube with chalk dust. It is simple. And it's very good for preparative work. What do we mean by prep? Prep is when we load a lot of sample onto a column, and then we collect a peak or one of the components because that's the product we want. But there are some disadvantages to this technique. It is slow. It is fed by gravity. It is low resolution. difficult to separate two compounds that are very similar, and it is very hard to quantitate. But people were excited because we have a technique now that will allow us to be able to separate. But what can we do to make this technique better, to make this technique more efficient? Well, one thing we could do is use a pump. And rather than gravity moving the liquid through the column, let's use a pump to push it through. Our columns, rather than using something that we grind up in a mortar and pestle and then pack, why don't we use very small particles that we pack under higher pressure? And then finally, instead of having to collect fractions and take them to some offline technique, let's bring a detector in line with the column, such as a UV-vis spectrophotometer. Well, when you use a pump to push the liquid and you use smaller particles in your column, you now produce pressure. And so this technique became known as HPLC, high pressure liquid chromatography. But the name we really prefer to use today is high performance liquid chromatography, because that's really what it is. Now, in today's world, you will hear people talk about two forms of LC, HPLC and UHPLC. HPLC is high performance or high pressure liquid chromatography. This is typically used for a lot of routine analytical work and is generally considered to be done at pressures under about 6,000 psi. If you're going to do UHPLC, or ultra high performance liquid chromatography, the type of hardware you're going to buy is a dedicated UHPLC system. And this is optimized to work with shorter analysis times, smaller particles, SPP columns, and higher flow rates. And as a result of this, it may run at higher pressures. So these systems can typically go up to about 18,000 psi. Now, why is HPLC the most widely used technique in the world? It's very simple. We have one requirement. Can you dissolve your sample in any liquid? If you can dissolve it, we then theoretically can analyze it by LC. Hence, HPLC is widely applicable. We have high resolution with our new columns and our pumps, allowing us to separate multiple components. We can do analyses in 3 to 10 minutes that used to be done over hours. We have very sensitive detectors, including a mass spec. The reproducibility of HPLC is unrivaled. No analytical technique is as good as LC. We can typically get peak area reproducibilities of under 0.5% without doing anything special. It is a quantitative technique, and it is very easy to automate. The result, of course, that you get is what's known as a chromatogram. On the y-axis, we plot the detector response, for example, absorbance. On the x-axis, we plot analysis time. The number of peaks you see in a chromatogram correspond to the number of compounds or analytes in your sample. The area or height of a peak tells you the concentration or the amount by, of course, comparison to a standard. And then also by comparison to a standard, we can use the retention times to tentatively identify our peaks. But this chromatogram shown here with 3 peaks could be of any 3 compounds in the world. So whenever we specify a chromatogram, it is important to always say, what is the column, what is the mobile phase, and what is the flow rate? Because on any HPLC anywhere in the world, if you use this column, 80% methanol water and 1 milliliter a minute, and you inject these 3 compounds, This is the chromatogram that you should see. Again, a very highly reproducible technique. So having given you a little bit of the theory, let's turn our attention now to the basic terminology of chromatography. And essentially, there are 7 terms we will talk about: retention time, void time, capacity factor, selectivity, resolution, column efficiency, and asymmetry. These 7 terms help us, and understanding them help us to do method development. But beyond method development, they also become very important in the routine analytical lab, because we will define limits for many of these, and we will run what is known as system suitability. So let's take a closer look and talk about what each of these are. Retention time. We use retention time to tentatively identify our peak by comparison to a standard. It is the amount of time it takes from when you inject the sample to when it reaches its maximum in the detector. So you measure from the point of injection to the retention time, or the top of the peak. Associated also with this is something known as the void time, or T0. This is the amount of time it takes for something that does not separate, that does not interact, to travel from the injector to the detector. Our next term is K prime, or capacity factor. This is a measure of retention. Every peak in a chromatogram has a K prime. The K prime is defined as the retention time minus the void time divided by the void time. Ideally, you would like your K prime values to be greater than 2. Why? Because that means your peak is interacting with the column and you are separating it. It is out of the void volume. The larger your K prime, the longer your retention time, the better the separation. But of course, there is a trade-off. We have work to get done. So usually in method development, we try to adjust the K prime to put it between a value of 2 to 10, meaning we get our analytes of interest to stick, but we also get them to come off in a reasonable period of time. Our next term is selectivity, or alpha. This is a measure of the separation of 2 analytes, how well they separate from each other. We determine the alpha value by calculating the capacity factor for each peak, and then taking the later eluting peak capacity factor and dividing it by the earlier eluting. Now, the disadvantage of selectivity is that it only looks at the retention time. It only looks at the top of the peaks. It does not look at what is happening down at baseline. So a better way to tell if you really have a good separation of your 2 peaks is to use the resolution equation. And here you can measure the degree of separation from 2 peaks by taking the retention time of the second peak, dividing it by the retention time of the first peak, and then measuring the width at base. And a good rule of thumb is you want, as a minimum, a resolution value of 1.5, because this means you have actually separated your 2 peaks to baseline. The larger the resolution, the better the separation of the 2 compounds. However, the larger the resolution, the greater the analysis time. There is a better way to look at the resolution equation in terms of doing method development, and that is we can express it as really being comprised of 3 terms: retention, selectivity, and efficiency. And what we try to do in method development is optimize each of these 3 terms. So let's look at it in a little more detail. Retention. How do we optimize our peaks sticking or interacting with the column? Well, the power of liquid chromatography is in the liquid. It is in the mobile phase. So we can work on achieving a separation by changing the mobile phase, by changing, for example, the pH, or the type of buffer we use, or the concentration of that buffer, or the amount of organic modifier, methanol or acetonitrile, we might add. Changing the mobile phase is easy, it's inexpensive, but method development is definitely time consuming. To optimize the selectivity, what do? Again, start with what's the least expensive and the simplest to do. Work with the mobile phase. Change the composition of the mobile phase. But if you just cannot pull the two peaks apart using the mobile phase, well, then you need to think about changing your stationary phase or your column. And this, of course, is more expensive because you need to buy a new column. Maybe a longer column of the same material. Maybe a column the same size, but with different particles. Maybe a totally different phase altogether. All right, but again, you change the column and then you work with the mobile phase again. Also, sometimes temperature can help you in your selectivity. Let's step aside a moment and talk about the role of temperature in LC. Personally, I believe every HPLC system should include a column oven. Why do I believe that? Because we want to have very repeatable and reproducible retention times, and controlling the temperature is very important for that. Also, changing the temperature might help improve the separation a little bit. Certainly, if you put your column in an oven and run at higher temperatures, you will reduce the viscosity of the mobile phase, which of course then lowers the pressure in your system. Additionally, you will improve the efficiency. You will get a more rapid mass transfer, maybe get a little less peak tailing, for example. But let's return back to our definitions. The last component of our resolution equation is efficiency. And to be honest, this is something you do not have a lot of control of. This is a function of the column. The only thing that you can really do to improve this term is to make sure you're running at the optimum flow rate for your column. But if you are at the optimum flow rate, that's where it ends. There's nothing else you can do. So again, if you need more efficiency, you might look at a longer column. You might look at a column packed with smaller particle size. Or you might even look at a different manufacturer, because not all columns are the same. Now, I mentioned efficiency. What do I mean by that? Well, basically, we call column efficiency N, or the number of theoretical plates. The greater the number of theoretical plates, the more likely the column will be able to separate the compounds that you want. One way to calculate it is the retention time divided by the width at base squared times 16. And again, the greater the number of theoretical plates, the greater the resolving power of your column. Related to the number of theoretical plates is another term known as HETP, height equivalent to a theoretical plate. The smaller the HETP, the better the column. So now if we take that and put it into practice, we can generate something that's known as a Van Deemter plot. This is not something you will ever need to do yourself or ever need to generate, but it is important to understand the two important messages that come out of the Van Deemter plot. and out of LC theory. So in a Van Diemter plot, we plot the height equivalent to a theoretical plate on the y-axis and flow rate on the x-axis. We have here a test compound, and basically we have 3 columns of the same length but different particle size. And then we've measured the HETP as we change the flow rate. Remember, the lower the HETP value, the better the column. So the first take-home message is a 3-micron column will always give you a better separation than a 5-micron column, and both a 3 and a 5 will always give you a better separation than a 10-micron column. So if you're just starting out in method development, or you're looking to further improve an assay, look at smaller particle columns. Message number 1. Message number 2, look at these curves. Let's take a look in particular at the 10 micron. All right, if you look at the 10 micron, you will notice that there is a minimum here. This is where you will get the best separation. This is in the range of roughly 0.8 to 1 mils a minute. So therefore, when you start your method development with a 10 micron column, if you are at 1 mil a minute, flow rate will no longer be a variable to affect the development of your separation. You can change the flow rate and it will get worse or faster, but it will never get better if your flow rate is set at a minimum. Again, the power of LC is in the mobile phase composition, not in changing flow rate. If you run a 5-micron column, again, if we look at the Van Diemter plot, we notice there's a minimum roughly here. This is between 1.2 and 1.5 mils a minute. Set your flow rate there, sit there, and that's where you will get your best separation. Do not play around with flow rate. It will not improve the separation. It will make it faster and worse, or slower and worse, but it will never make it better. Work with the mobile phase composition. Now, what happens when you look at your faster flow rates, then you're going to be dealing with higher pressures. And that's why UHPLC is becoming such a common and popular technique. The last parameter that I want to talk about in terms of terminology is peak asymmetry. All peaks in chromatography are supposed to be, according to theory, Gaussian. If you cut them down the middle and fold them over, they should lay on top of each other. That's theory. That's not reality. In fact, most of the time, you will observe some peak tailing. You might see peak fronting, and that's typically due to too high a concentration or overloading your column. But we will almost always see some peak tailing, and that's due to the interaction of your samples, the competition between the mobile and stationary phase. A certain amount of peak tailing is acceptable, and often values between 1 to say 1.2 or 1.3 will be defined as acceptable. So now that we understand a little bit about the terminology in chromatography, again, for system suitability, what we can do is you can define values for 1, 2, or all of these parameters. And then every morning you can run your standard, calculate these values, and see if they are in the acceptable range. If they are, your system is now suitable to run your assay that day. So again, this terminology helps us for method development, but it also helps us for routine operation. Let's talk about the various modes of column chromatography. I'm not going to spend a lot of time here because at the end of the month, we will present our second webinar in this series, which will focus on column selection. But to give you an introduction, there are 4 main modes of chromatography: normal phase, reverse phase, ion exchange, and size exclusion. Normal phase is historically what existed first. Your stationary phase will be polar, something like silica or alumina. Notice that silica has hydroxyl groups on it. That's what makes it polar. Your mobile phase or your liquid will be nonpolar. Your weak solvent will be hexane or heptane. Your strong solvents will be things like methylene chloride or chloroform. And we will use this technique to separate polar compounds. Your nonpolar compounds are not attracted to the column, so they will elute first. And then as your compounds increase in polarity, they will stick to the column more and elute later. The mechanism of separation for normal phase is generally then adsorption or desorption. This is an excellent technique for isomers or group separations or even for sample cleanup. You have to be careful of 2 things, though, regarding the mobile phase. First off, water may change or ruin your column. And second, as you've seen, the solvents we use are pretty hazardous or toxic. So ideally, your LC should be under a vent or in a hood. Now, the most popular form of LC is without a doubt reverse phase chromatography. And this is the opposite of normal phase. Here, our column or our stationary phase is nonpolar. So we can take the same silica we used, but now we chemically bond a chain of carbon atoms, for example, 8 carbon atoms, or C18, 18 carbon atoms. Our mobile phase will be polar. Water is the weak solvent or a buffer, and methanol or acetonitrile are the strong solvents. And again, we're going to separate here now nonpolar compounds, which is most of the compounds that are out there in the world. Your polars will elute first, followed by the nonpolar compounds. The separation mechanism here is a partitioning or a weak hydrophobic interaction between the mobile and stationary phase. We love reverse phase chromatography because the elution order is predictable. It has the most stable and advanced column technology, and it is applicable to many small molecules. This is an example of a test mix that we will use here at PerkinElmer to verify that our systems are working properly. Again, it's a C18 column, methanol water mobile phase, 2 mils a minute. Our third mode of chromatography is ion exchange. You can do anionic or cationic ion exchange. Are you separating positively charged or negatively charged compounds? Your column or your stationary phase could be a polymer or a silica support that has some kind of ionic charge group chemically bonded to it. You will be separating compounds based on charge or ionizability. So therefore, your mobile phase will be a buffer. So the separation is going to be based on an ionic interaction. You can use some organic modifier, but sometimes you have to be careful because too high a concentration of methanol or acetonitrile might precipitate out your buffer. And some common applications for ion exchange are amino acids, inorganic ions, polynucleotides, and proteins. The last mode of chromatography is very different than the other 3, and this is called size exclusion chromatography. There are two forms, GPC, gel permeation chromatography, where your mobile phase is almost always tetrahydrofuran, and then gel filtration chromatography, which is aqueous-based size exclusion. And this technique is very different. There is no chemical interactions here. This is a physical separation technique. So you really use only one mobile phase. You control the pore or the size of the holes in your stationary phase. And your molecules travel in and out of those pores. So again, this is a physical separation technique. The separation is based on the size and shape of your compounds. This is very different, again, than the other forms, because here, your large molecules will always elute first because they cannot penetrate the pores. And the large molecules will then be followed by smaller molecules. Size exclusion chromatography is often used to determine molecular weights. And from these molecular weights, we can determine physical properties of polymers and biomolecules. And this is the one form of chromatography where temperature control is absolutely critical, because you're generally dealing with larger molecules, and you want to be sure you lock in the conformation so that they're not going back and forth between different forms. Just to demonstrate the point, here is an example where we are separating phthalates. And again, the larger phthalates come out first. The dioctyl first, followed by the dibutyl, followed by the diethyl, followed by the dimethyl. And that's about all I really want to say today about column selection. Again, we will be presenting another webinar at the end of the month that will talk in much more detail about columns. So let's now turn our attention to a brief discussion of HPLC and UHPLC hardware. This is a general schematic of an LC system. So you have your solvent reservoirs where your mobile phase is. The liquid goes from your mobile phase to the LC pump. From the pump, it then travels to your autosampler or your manual injector. From there, it goes to your column, which is the heart of the LC, where the separation occurs. That column may or may not be in an oven. Your separated peaks then leave the column and go to the detector, and then the detector sends your signal to the data handling system. So what we're going to do is start at the beginning and walk through each of the components in the LC system. What are some of the important properties of the mobile phase? First off, the sample must dissolve in it. You want to use high purity solvents, HPLC or LCMS grade. Your mobile phase should be non-corrosive. Hydrochloric acid is generally not a good mobile phase with a stainless steel system. You want low viscosity. Isopropanol is a fantastic solvent for reverse phase. However, the pressure would be so high. If you're using a UV detector, you want your mobile phase to not interfere. Toxicity, we always worry about our own health and our exposure to chemicals. Low cost, not just to buy the solvents, but also the waste disposal of the solvents. And ultimately, you want your mobile phase to be able to separate your peaks, to give us K prime values between 2 to 10. An important thing in running an HPLC system is cleanliness. You should always filter all organic and aqueous solvents or mobile phases through 0.5 micron filters. Every HPLC vendor will also include with their system fritted filters or sinkers that sit in the bottom of the bottles to prevent bigger particulates from getting in. And some of the vendors will include, after their pump, a 0.5 micron filter in line to, again, further make sure that contaminants, particulates, do not travel further into the system. Now, one other thing is all mobile phases have dissolved oxygen in them. You always want to remove the oxygen from your mobile phase, because if you put that liquid under pressure, you could force the air bubble out. The air bubble will be stuck in the pump. It will expand and contract, which affects your flow rate, which now affects your retention times and your ability to correctly identify your peaks. So there are a number of techniques that we can use for degassing, but by far the most popular one used today is the online vacuum degasser. This literally pulls a vacuum on the outside of a piece of tube and sucks the oxygen out of the mobile phase as it is passing through the tube. I always like to show this chart because it's a nice chart that summarizes mobile phase. If you begin at the top at N-hexane and move downward to tetrahydrofuran, you are looking at some of your typical normal phase solvents in increasing solvent strength. If you start at the bottom with water, and again move up now to tetrahydrofuran, you are looking at your reverse phase solvents in increasing solvent strength. The other thing I like to point out in this chart is the viscosities. Again, notice in particular the very high viscosity for isopropanol, and everything is based on looking at water. And then it also summarizes some of the UV cutoffs. We will also sometimes add additives or modifiers to our mobile phase. Buffers, acids or bases, ion pair reagents, for example, tetrabutyl ammonium hydroxide or hexane sulfonic acid. Moving on to the next component of our system, let's talk about the pump. The requirements for the pump are that it gives us precise and pulse-free delivery of the mobile phase. The pressures for an HPLC are typically up to 6,000 psi. A UHPLC can go up to 18 or 20,000 psi. Most of us will be operating in the analytical flow rate range, and that means we'll be operating somewhere between 0.1 to 5 mils a minute. We would also like our pump to be chemically inert, not add any peaks to our chromatogram, be able to do gradients, and be easy to maintain and service. Now, what do I mean by elution? There are two ways to elute the peaks from your column. An isocratic separation, we pump the same mobile phase the entire analysis time. In a gradient separation, we will change the composition of the mobile phase over time. Here we're running for 100 minutes. We started at 0% of the solvent, and in a linear fashion, we changed to 100%. Roughly 40% of all separations are isocratic, but again, gradient is very, very common. Now, all of our pumps typically operate on a reciprocating pump mechanism, meaning you have pump seal is to keep the liquid, the mobile phase, in the liquid end of the pump and prevent it from traveling backwards. The pump seals are usually what needs to be changed on yearly maintenance. Now, there are really two types of pumps out there today: high pressure mixing pumps and low pressure mixing pumps. In a high pressure mixing pump, you have two or more pumps, and you combine the solvents in a mixer or T after the pump. Low pressure mixing systems are the more common, and here you have one pump with a proportioning valve or a solenoid, which is used to blend the solvents. Here is a schematic of a high-pressure binary mixing system where we have two pumps. Each of them will have a different solvent at a different flow rate, and they will combine in the T and then go on to the injector. Again, the mobile phase components combine after the pump. This is an example of a low-pressure mixing system. This happens to be a schematic of the PerkinElmer Flexar analytical pump. Here it's a quaternary system. You have 4 solvents, A, B, C, and D, and they combine here in a proportioning valve, and then they go on to the piston. So that's what we mean by a low pressure mixing system. Let's talk about how we introduce our samples. Well, we have an injection valve. This is a 2-position valve, inject and load. It consists of the valve, a rotor, a sample loop, and a needle port. And this allows us to introduce our sample under high pressures without interrupting flow to the column. That's very, very important. We generally do not pierce through anything in an LC autosampler like you do in GC. In GC, you pierce through a septa. Here, we generally do not do that, and we will typically use a blunt tip syringe. What is an autosampler? It is a system where there is a motor on this injection valve to move it back and forth between the inject and load positions. And again, with today's autosamplers, without doing anything special at all, except running them properly, you can get RSDs for peak area of under 0.5%. No internal standardization or anything like that required. Again, a very reproducible technique. Columns. Again, I won't dwell on this much, but I do want to talk for a moment about hardware and length and diameter. There are different types of columns. There could be a standard column or a cartridge column where you have a holder and you can just buy refills for it. The columns could be made of stainless steel or PEEK, polyether ether ketone, glass, or titanium. These columns will have end fittings, which are and have frits in them of 0.5 micron. The frits keep the packing in the column, but also keep the junk out of the column. And then you'll have nuts and ferrules and connecting tubing. For HPLC, our connecting tubing will typically be 0.007 internal diameter or smaller. For UHPLC, you'll typically use 0.04 or 0.05. Now, people often ask, why do you sell columns of the same material in different lengths? And I'm just going to try to answer that here. Here's the 3 compounds we're interested in separating. If you have to run 100 samples a day, then the 3-centimeter column is the correct column for you because you need speed. On the other hand, if you're running a very complex sample and there are a lot of other compounds that might elute in addition to the 3 of interest, then you need a column which has a lot of theoretical plates, a lot of resolution. So therefore, the 22-centimeter column would be the best column for you. The final component we need to talk about in the LC system, hardware-wise, is the detector. There are a variety of detectors for LC. The UV and the photodiode array detector are the most common. And again, I'm not going to dwell on this topic here because in October, we will do a webinar strictly dedicated to a discussion of the properties and the type of detectors and which one might be best for your assay. But we have UV detectors, fluorescence, RI, mass spectrometry, and so on. Of course, the final piece is you need to have a data handling system, some way to look at your chromatogram. This could be a strip chart recorder, It could be an integrator or a workstation, or it could be a full-blown network with all kinds of security. Again, we're not going to spend any time talking about this here. There have been many dedicated webinars already talking about data handling systems, but the bottom line is you need to see your chromatogram, maybe you need your retention times, and maybe you need your peak areas and quantitation and reports. There are a number of accessories for HPLC. I did talk about one being the column oven. Personally, I think every system should have it, so I don't really consider it an accessory. There are column switching valves for method development and high throughput, fraction collectors, and much more. But we don't have time to talk about them in more detail. And again, as I've said, HPLC is everywhere. If you can dissolve the sample, we can analyze it. The biggest market is, of course, pharmaceuticals, followed by food applications. But there are applications in life science, in the environment, in plastics, and in chemicals.